Hi everybody. In this lecture we're going to be discussing heat and matter. So in previous lectures we've talked about atoms and molecules and how atoms and molecules come together to form compounds. So now we're going to be talking about how these atoms will be interacting with one another. So let's move along and see what we've got. Let's start with first with matter. What is matter? Matter is anything that occupies space and has mass. In other words, anything that has density. If it has mass and takes up space, it is considered matter. So then what is not considered matter? Well, an idea would not be considered matter. Energy is not matter. So all of the forms of energy, things like heat, light, sound, those things are not considered matter. Matter has mass and matter takes up space. Now notice that I've chosen something to put here that is, some people think doesn't have mass. Air. Air absolutely has mass because of the fact that if air did not have mass, then you would have greater pressure inside you than outside you and you would explode, and so that probably wouldn't be a good idea. Air most definitely has mass. The law of conservation of matter tells us that matter is neither created nor destroyed, it only changes form. And really, matter and energy work together like this. Matter and energy are not created, they only change form. The forms of matter, solid, liquid, and gas, and then plasma are the primary states of matter. Now, how often are you going to come into contact with plasma? Probably not. Because you've got plasma is a completely ionized gas, and it's just not one of those things that you come into contact with on a regular basis, although I mean we do have it on Earth and whatnot like that, but mostly we see plasma, and stars are made of plasma. They're not fire or anything like that. It's it's plasma, it's ionized gas. But solid, liquid, and gas, that's what we're going to focus on most likely, because that's what you're going to come into contact with most often. Kinetic molecular theory. So let's see, what does this say? We know that matter is composed of atoms or molecules if those atoms are together. So those tiny atoms and molecules interact physically with one another and they're separated by empty space. Okay? All of them are in constant motion. Well, what is motion? But motion is kinetic energy. So when we think about matter, whether we're talking even things that we consider solid, like a piece of wood or a piece of metal, it's made up of atoms that are in constant motion. They are in constant motion, and that is full of kinetic energy. The more kinetic energy it has, we can measure that, because kinetic energy will translate into heat. So kinetic energy increases heat as it is added and decreases heat as it is removed. So whenever you heat something up, all of those atoms and molecules, depending on what kind of substance it is, are going to be moving faster. So we'll just say particles, so that we don't have to say atoms and molecules all the time. So all the particles that make something, that compose something, as you heat it up, they will move faster. So more kinetic energy translates into heat. Okay. Less kinetic energy means that something is cooler. So let's take a look at our phases of matter. To start with, solids. Solids have a definite shape and volume. Okay, in other words, it has a rigid 3D structure. All of the molecules are bonded into place, although they are still vibrating, but they are restricted to vibrating in one particular place. Okay, and they have the least amount of what is referred to as entropy. And what is entropy then? Entropy is disorder. So if something has low entropy, that means it has a low amount of disorder. If something has high entropy, that's a high amount of disorder. Solids have the least amount of disorder because all of their particles are locked into a crystal structure. And so you have, sorry, my cat's right here. They're locked into a crystal structure, and because of that crystal structure, they can only vibrate in certain ways, and so there's not a lot of disorder. So if we think about that, think about this model here with little balls on the end of springs. So they're connected by springs to other balls, and so they can only vibrate in certain ways. So if we take a look, like this ball right here can only vibrate in certain directions. It's limited to where it can vibrate because of the fact that it's connected with the springs to the other balls, and so it has the least amount of disorder. Liquids. Liquids have a definite volume, but they have an indefinite shape. Well, that makes perfect sense. Think about it. I can take a liquid and I can pour it from one container into another. I don't change its volume. If I have 250 milliliters of water in one container and I pour it into another container, it's still 250 milliliters, even if that container has a different shape. But the liquid has a different shape. The particles that make up a liquid have weaker cohesive bonds between them than do solids. And so the molecules slide past each other. That would be the fluid nature of a liquid. Compared to solids, they have a moderate amount of entropy. So they have a little bit more disorder. So they have more disorder than a solid. Okay, so liquids have more disorder than a solid because they have vibrational motion and they also have rotational motion. If we think about our same model, you still have connections between particles, but they're not connected to all of the particles that are around them, so that they can slide past each other. So again, these particles can slide past each other. They have more entropy than did the solid, but they have less entropy than do gases. Gases have both an indefinite volume and an indefinite shape. Gases will expand to fill a container, or they can also be compressed. You can't compress a solid, you cannot compress a liquid, but you can compress a gas. In a gas, the molecules or the particles, depending on whether we're talking about a molecular gas or an elemental gas, the particles in a gas are primarily not in contact with each other. From all of the common phases of matter, gases have the most amount of entropy. In other words, they have the most amount of disorder. So think about gases are just in constant motion. Okay, they vibrate, they rotate, and they move randomly in all sorts of directions. They have random paths. Okay, so they're not connected to other particles, and so they can move in any direction they want to. Well, it's not want to. They move in any random direction, and that randomness gives the gas the most amount of entropy for our common phases of matter. So gases have the most entropy. Now, what was entropy again? Disorder. So gases have the most disorder, entropy. Liquids have less entropy because they're connected to each other. They will slide past each other, but they're still connected to each other. They have some cohesion there. And then solids have the most amount of cohesion, the most amount of order. That means they have the least amount of disorder, so the least amount of entropy. Now, plasma. Plasma is a different case altogether. This is a very hot gas in which all of the electrons have completely been blown off of it. So you have this completely ionized gas, or most of the electrons have been stripped of the electrons because of high kinetic energy. And so it just behaves completely different from other things. And so I guess you could say that it has the most amount of entropy. But let's talk about what happens when something changes from one phase of matter to another. So if we take a look at this is called a phase diagram, okay, or a heating curve. Whenever we have this heating curve, if you look across the bottom of your heating curve, the x-axis, constant heat input. So in other words, we're continuing to add energy. Along the y-axis, the vertical axis, this is the temperature in degrees Celsius. So if we take a look, if we're warming, let's say that we start with ice at negative 20 degrees Celsius. Look at what happens. As we heat the ice up from negative 20 degrees Celsius to 0 degrees Celsius, you can see the temperature is changing. Okay, obviously as we go from left to right, I've added heat. And because I've added heat here, I can see that the temperature has increased from negative 20 to 0 degrees Celsius. Okay, so that's warming it up. So it's continuing to heat as I warm up. Now, look at what happens from here to here. Notice what that line is flat. So it's all 0 degrees Celsius. But I'm still got a constant heat, increasing heat energy. So where did that heat energy go? If it's not being used to increase the temperature, what's it doing? Well, it's changing the phase. It's actually changing this dihydrogen monoxide, that's changing the water from a solid to a liquid. So in this part of the graph right here, until every bit of it becomes a liquid, all of that energy that's going into it, and you can see we're still adding energy because it's a constant heat input from left to right. All of that energy is going into melting the ice. So let's think about what we have here. In this first section, all we have is ice. But in this second section right here, we have ice and water. So we're changing phase. This is a phase change. No change in temperature. Now, once everything has become water, see this whole section right here is nothing but liquid water, as we continue to add heat, the temperature increases and we go from 0 degrees Celsius to 100 degrees Celsius. Well, what happens at 100 degrees Celsius with water? It starts to boil. Well, what's happening to this when it boils? Well, when water boils, what is happening is it is going through a phase change. It is being converted from water as liquid to water vapor. So you have phase change again. Now look at the temperature. I'm still adding heat, but did I add any temperature? Did I change the temperature? No, I didn't change the temperature, because what all of that heat energy is doing is it's going into changing it from one phase of matter to another. It's changing it from a liquid to a gas. Then once all of it is a gas again, now my temperature can start going up again. And here I have nothing but water vapor. So the temperature doesn't change whenever we're changing from one phase of matter to another. The temperature only changes when I have one phase of matter that's in my sample. The temperature changed here, where I have just ice. The temperature changed here, where I have just liquid water. And the temperature changes here, where I have only water vapor. But in both cases, when I'm changing from one phase of matter to another, like here from ice to water, and here from water to water vapor, I have no temperature change. What's actually happening here is all of that energy is going into changing it from one phase of matter to another. Well, let's put this together with what we know about entropy and kinetic energy. As I'm continuing to add heat energy to this, I'm continuing to add kinetic energy. Well, here I don't measure that change in kinetic energy, because what's happening is I'm changing phase. But when I'm actually moving to a higher temperature, I'm adding kinetic energy. Those particles are moving faster, and that can be measured as a change in temperature. So I have the least amount of entropy here. I have more entropy here, but less than down here. And then I have the most amount of entropy up here in this, when it's all water vapor. So the most disorder, moderate amount of disorder, and very little disorder. So very little entropy, a moderate amount of entropy, high amount of entropy. All right, so we can take a look at that here in a slightly different way. Here, solid ice, and I can only move in certain directions. I melt. melt things. It absorbs energy, and so when I absorb energy, we get a liquid. The liquid has a definite volume but an indefinite shape, and those particles can move past each other. I continue to absorb even more energy, and so what we end up with is a gas. And the gas has the most amount of entropy. So increasing molecular potential energy, increasing energy absorption, okay, increasing entropy as I go from left to right. Now, if I release energy, just the reverse happens. If we release energy, we reduce the amount of molecular potential energy, also reduce the amount of kinetic energy that's going on here. And so what happens is we take this gas and it condenses into a liquid, and then it freezes into a solid. So we go from, as we reduce the amount of kinetic energy, we go from a gas to a solid. So we're releasing heat, releasing energy as we move from the right-hand side of this graph to the left-hand side of this graph. So let's take a look at what each of these phase changes would be called. Okay. Temperature. As you're increasing temperature, we go from a solid to a liquid. The common name for that is melting. The chemical name for that is called fusion. Liquid to a gas, common name is boiling. The chemical name is vaporization. Now, there are some things that can go straight from a solid to a gas, like dry ice, solid carbon dioxide. When it goes directly from a solid to a gas, that is called sublimation. Okay, that is called sublimation. Now, going in the opposite direction. If we go from a liquid to a solid, we call that solidification, or the common name is freezing, but it's solidification. If we go from gas to a liquid, that is condensation. If we go from gas directly to a solid without going through the liquid phase, we call that deposition. Deposition is how we get snow. When you have water vapor that is transformed directly into a solid rather than going to a liquid phase. And here you can see those, each of those names in this diagram here. Going from a solid to a liquid. Solid to a liquid is melting. Liquid to solid is freezing or solidification. Liquid to a gas, vaporization. Gas to a liquid, condensation. Solid directly to a gas is sublimation. Gas directly to a solid is deposition. And this is all looking at the enthalpy. Now, this is a different word. Enthalpy. Now, we can use context clues and figure out what enthalpy is. What am I actually increasing going from a solid towards a gas? Heat energy, right? That's what enthalpy is. Heat energy. So we've got two words that sound very similar, but that mean something completely different. Entropy is the amount of disorder. Enthalpy is the amount of heat. So enthalpy is heat energy that we're putting into a system. So as we increase the enthalpy going from here to here, we will go from a solid to a gas, and sometimes it goes through a liquid and sometimes it goes directly there. As we decrease the enthalpy, we're going to go from a gas to a solid either directly or by way of a liquid. Evaporation and condensation. Individual molecules can change phase at any time. Okay, evaporation, it requires energy to overcome the cohesion. Cohesion is the amount of connection that an atom, or attraction that an atom has to other atoms of its own type, particles of its own type. So when one water molecule is attracted to another water molecule, that is cohesion. When water molecules are attracted to something else, we refer to that as adhesion. So in order for water to evaporate, it has to have enough energy to overcome the cohesive pull of the other water molecules. Once it does that, then it will evaporate. So higher energy molecules are near the surface, and so they escape. When you boil water, you're actually putting more energy into it, and so you're getting more and more molecules that are coming off the top, and they're becoming a gas during evaporation. Condensation goes in exactly the opposite. So gas molecules lose kinetic energy and condense to form a liquid, and they will merge together to form bigger and bigger drops of a liquid. So in order for condensation to take place, gas molecules will lose energy, and they become a liquid. So here we see this in the form of a graphic. So these molecules, the molecules of water that are closest to the surface, will have more energy, and so it's easier for them to escape, and in other words, evaporate. And then when molecules are condensing, molecules that are closest to the surface are going to condense. Or if this is a drink that has ice in it so that it's cold, or even if it's not a drink, if it has ice in it and it's cold, the molecules of moisture that are closest to this are going to lose energy as they come into contact with the cold glass or cold surface, and the water molecules will condense on the glass. That's why when you have, like, if you have a cold, like an iced tea, and you're sitting outside and it's humid, water is going to condense on the outside of that glass. That's because as water vapor comes into contact with that cold glass, the water loses kinetic energy. Water vapor loses kinetic energy and condenses on the glass. So what is heat then? Heat is a unit of measure, or heat is, a unit of energy. Heat is energy. We're going to measure heat in two different ways. We have the calorie and we have the joule. Well, this is cal with a lowercase c, and that is the amount of energy that is needed to raise 1 temperature of water, or 1 gram of water, 1 degree Celsius. Now, the equivalent amount in joules would be 4.184 joules. It takes 4.184 joules of heat in order to raise 1 gram of water 1 degree Celsius. Now, don't confuse this with a food calorie. A food calorie, now this is capital just because it's the beginning of the sentence, but a food calorie is a capital C no matter where you put it, and that is the equivalent of 1,000 calories, heat calories. So 1 food calorie is equal to 1,000 heat calories. So when you look on the label of a food item and it says contains 120 calories, literally what that means is it's 120,000 heat calories. And that heat calorie we define as the amount of energy necessary to raise 1 gram of water 1 degree Celsius. So heat is a form of energy transfer. Okay, it's a form of energy. Heat will always move from an area of high temperature, high heat, to low heat. Okay, and heat and temperature are not the same thing. Heat is energy. Temperature is a measure of that. Temperature is a measure, technically, of the average kinetic energy in an object. Heat energy will move from an area of high concentration to low concentration. So in other words, from something that's hot to something that's cold. So if you reach down and you touch something that's hot, the heat energy is going to move into your hand that's cooler rather than being pulled out of your hand. Now, if you grab something that's really cold, heat will be pulled out of your hand and heat will go from your hand to whatever is cold. That's why if you put a piece of ice in your hand, the piece of ice is going to melt because it's drawing heat energy from your hand. So temperature is a measure of the internal kinetic energy, the average internal kinetic energy of an object. Okay, we use a thermometer to measure that. So temperature and heat, again, not the same thing. Heat is energy. Temperature is a measure of that energy. Typically in science, you will use Celsius or centigrade. where water freezes at 0 degrees and boils at 100 degrees. This makes things really simple when you're working with temperatures in the science lab. Degrees Fahrenheit, water freezes at 32 degrees and boils at 212. So there's not really an awful lot of logic there. So degrees Fahrenheit and degrees Celsius are two different temperature scales. Temperature is a measure of the average kinetic energy in an object. Water. Water everywhere, not a drop to drink. Okay, water is a major constituent of everything, most living things, and we talked, if you recall from a couple of some of our other lectures, we talked about the fact that you need water because all of the chemical reactions that are going on in your body take place in an aqueous solution. So that's why you have to have water. Water is typically referred to as a universal solvent, even though we've never been anywhere else in the universe. But we call it the universal solvent because of the fact that it will dissolve most things. Since we say that like dissolves like, water is a polar covalent molecule. Covalent because it shares electrons between the hydrogen and the oxygens, but it's polar because one side of the molecule is positive, the hydrogen side, and the other side of the molecule is negative, the oxygen side. Because part of it is positive and part of it is negative, we say that it is polar. It has a positive side and a negative side. This means that it will dissolve any ionic compound, because ionic compounds are also positive and negative. Well, since most elements in the periodic table are metals, metals form ions, they form ionic bonds. So what this tells us is that most compounds on Earth will dissolve in water. That's why we call it the universal solvent. So whenever when we're talking about water, one of the things that we have to talk about is that its solid phase is less dense than its liquid phase, which is why ice floats on top of water. We use water as a definition for a calorie, its specific heat, the amount of heat that is necessary to increase 1 gram of water 1 degree Celsius is equal to 1 calorie. Okay, equal to 1 calorie, and we use water as the way that we are defining that. Water is highly cohesive. It will attract other water molecules, and it also has adhesion, which means that it can be attracted to other molecules. It has a stronger cohesion than adhesion. Heat flow. So there are 3 different ways that heat can move from one object to another. Okay, remember what we said. Heat will move from an area of high concentration to an area of low concentration. Well, heat can move by 3 different ways: conduction, convection, and radiation. So it will always flow from an area of high concentration to an area of low concentration. In other words, from a high temperature to a low temperature. So let's take a look at each one of these different types. Conduction. Conduction happens when you actually have physical contact, heat flowing through matter. If I touch a hot piece of metal, my hand will get hot. That is heat transfer by conduction. If you're actually touching it, that's heat transfer by conduction. So hot atoms combine or collide with cooler atoms, and then that kinetic energy is transferred from one to another, and so the heat is transferred. Direct physical contact is required. Okay, direct physical contact is required for conduction. Things that are not good conductors will not transfer heat. That's why we make insulators out of styrofoam and wool and such like that. So your coolers have an air layer of insulation to prevent transfer of heat. Okay, but what should we know from this? Conduction. Heat transfer by conduction is direct physical contact. Okay. Convection. Convection is transfer through a fluid of some sort, either a liquid or a gas. You've probably heard of a convection oven. Well, in a convection oven, heat is transferred to whatever it is that you're cooking by way of circulating hot gas. So when you transfer energy by way of a moving fluid, whether that fluid is a liquid or a gas, it is referred to as convection. Now, you probably heard of convection currents. Okay, a hot gas will be less dense than a light gas, and so it will rise. And a cool gas is more dense than a hot gas, and so it falls. So if you have uneven heating, then the gas will form what is called a convection current. And convection currents really are what cause the winds on the earth, unequal heating of our atmosphere. So natural convection mechanisms, we have a hot fluid rising and a cold fluid sinking, which is what I was just saying.